For this problem, I want to look at the conversion of a couple of three-point networks, specifically the delta-connected and Y-connected three-terminal networks, and the conversion of one to the other. For this example, we'll be looking at resistances in a three-point network. However, the same process can be used for passive impedances, inductance, and/or capacitance. Let's first look at converting a Y-connected network into a delta-connected three-port network. Delta networks are also known as pi networks, both in reference to the Greek letters which mimic the shape of the network, and a Y network are also known as T networks, as shown here. A true equivalent circuit would represent the same resistance between any two terminals as the original circuit. Looking at the delta circuit, between the 2 points X and Y, the resistance would equal RA in parallel with the quantities RB in series with RC, and the 2 points XZ, the resistance would equal RB in parallel with the quantity RA plus RC, and the 2 points ZY, the resistance would equal RC in parallel with the quantity RB plus RA. In the Y configuration, the resistance between the same 2 points XY, the resistance would be RD plus RE. Between the 2 points XZ, the resistance would equal RD plus RF, and between Z and Y, the resistance would equal RE plus RF. Assuming that we convert the delta to the Y equivalent, then RXZ will equal RA in parallel with RB plus RC, RXZ would equal RB in parallel with the quantity RA plus RC, and RZY would equal the quantity RC in parallel with RB plus RA. Note that we have three equations now and three unknowns. RD, RE, and RF. We know RA, RB, and RC. Thus we can solve these three equations, using a term of elimination process. If we subtract equation 3 from equation 1, we eliminate the second resistance, RE, and arrive at the difference between the first and the third unknown resistances, RD minus RF. Now, let's bring down equation 2 and add it to the results we have from the previous subtraction, and we get 2RD is equal to RA in parallel with the quantity RB plus RC, plus RB in parallel with the quantity RA plus RC, minus RC in parallel with RB plus RA. Let's expand the three parallel terms on the right-hand side of the equation. That would give us 2RD is equal to the sum of three fractions you see here, all over the same denominator, RA plus RB plus RC. For the reverse process of converting Y to delta, we start with the expression for RD, RE, and RF in terms of RA, RB, and RC, and we will designate them as equations 4, 5, and 6. If two of these equations are divided, a single equation for RA, RB, or RC will result. For example, using equation 4 and 5 gives us this equation. The common terms in the numerator and denominator cancel out. The quantity RA plus RB plus RC and RA, leaving us with just RD divided by RE is equal to RB divided by RC. We can rewrite this equation and now get the equation for RB, which is equal to RC times RD divided by RE. This time we will use equations 4 and 6, giving us this equation. The common terms in the numerator and denominator cancel out. That is, the quantity RA plus RB plus RC and RB, leaving just RF divided by RD, which equals RC divided by RA. And we can rearrange those terms, and we get RA is equal to RC, RD divided by RF. Using equation number 4, we can replace the quantities RA and RB. RD would then equal this quantity. Dividing both sides of the equation by RD simplifies the equation slightly to this. Now dividing both the numerator and denominator by RC further simplifies the equation to this. I'm moving the final equation to the top of the page to give me more room for further maneuvering. I am also going to rearrange the fraction a bit to this. Including cross multiplying, which puts the numerator of a larger fraction on one side of the equation and the denominator on the other. We then again cross, which is the same as multiplying both sides of the equation by RF times RE. And the equation becomes this. We can remove the denominators of both fractions on the right-hand side of the equation because they cancel out the terms in their numerators, simplifying the equation to this. We now rewrite the equation, dividing both sides of the equation by RD, which gives us a solution for RC. And through similar sets of calculations, we can find a solution for RA and RB. So we now have a way of creating a delta arrangement for resistors in terms of the Y arrangement. So, summarizing, we have a method of converting a delta configuration of impedances into a Y configuration of impedances, and a method of converting a Y configuration of impedances into a delta configuration of impedances. In the first case, on the left, we know RA, RB, and RC, and we have the equation to find RD, RE, and RF. Subsequently, on the right, we know RD, RE, and RF, and we have the equation for finding RA, RB, and RC. This brings us to the end of this problem and its solution. If you want the full range of problems and their solutions, you can find them at my Stan store at this web address. But don't go away just yet. I want to take this opportunity to introduce you to a one-time offer coming from 𝐃𝐈𝐒𝐂𝐋𝐀 just in time for Father's Day. Simply copy this web address into your browser and it'll take you to the Anchor site that is offering up to 50% savings on Anchor products.